Okay, so we're going to start off by looking at 4.4, which is the last section in chapter 4. Most of this chapter was on rational functions, which is functions that are fractions. Okay? Radical functions are functions that have roots in them. Okay, and we're going to learn there's a pattern. Okay, generally when you're graphing these, which we are going to do a little graphing, even roots have a certain look to them, and odd roots have a different look. How do you tell if it's even or odd? You just look at the number that's right there. Okay, that number is called the index.
Wait, didn't you do this geometry?
Maybe you studied square roots a little, I'm not sure.
I think so. I think we did this in this bad.
Okay, so any expression of the form, this root symbol with a number written in there, okay, and that number is always going to be positive and it's always an integer. That's called a radical expression or a radical. Okay, it's important that the index, okay, that number that I circled, that n, it cannot be a fraction or a decimal, okay, and it can't be negative. So it's a positive integer. Okay, so that whole thing that I just put a box around, that whole thing is called a radical. The thing that I circled specifically, that's called the index. What's under the root, okay, the thing I put a wavy box around, that's the radicand. Okay, whatever's under that thing that looks like a check mark symbol there, that's your radicand. And the actual thing that I drew here, that's the symbol itself. That's the radical sign. Okay, so the radical, that's the whole expression. The index is just the number that's written inside that little check mark. And the radicand is what's under the root. Now, if there's no number in that, does anybody know what number we assume? 2. Okay, a lot of times you assume 1 in math when there's no number, but if you do something like this, you're assuming square root. So it's a 2. I don't really think it would make sense to have that number as a 1. That wouldn't even really make sense. Okay, but anything 2 or higher. So it has to be greater than 1. Questions on any of those terms? Okay, so the kind of things we're going to do with radicals, we're going to solve some equations, and then we'll also do some graphing. Okay, so we just said that a second ago. If there's no index, you assume it's 2. And there's another way to write something like that. Does anybody know how you can write a square root as an exponent? You can put a certain exponent right here, and it means exactly the same thing as square root.
Isn't it like -2 or something like that?
So a negative would cause it to flip. So we do use negatives, but not in this case. Negative exponents cause it to flip. These kinds of exponents cause roots. Yeah?
Is it like a half?
Half, yes, fractions. Okay, so you could try it on your calculator. Okay, on the left, we already know if you take the square root of 9, you would get 3. If you take 9 to the 1/2 power, you get 3. It's a square root of anything. Whatever you want to take the square root of, if you don't want to write it using the square root symbol, you can just take that and raise it to the 1/2 power. Now, any guess what exponent we would use for cube root? What? Yeah, 1/3. Okay, so if you had a cube root of something, you would raise it to the 1/3. What if you wanted to do a 5th root? What would be your power there? Yeah. 1/5. If you wanted to do a 10th root, 1/10. Okay, whatever the root is you're taking, it's 1 over that for the exponent. So in this last one, 5th root, I can take the radicand, which is what I had under the root, and raise it to the 1/5. Now this last one is a little special because there's something you can simplify. Okay. All the other ones had radicands with 2 terms, an x and a -2, x squared and a -1. This one just has x to the 4th. So now we have a rule with a power to a power. Does anybody remember what you do with the 2 numbers?
Multiply them together.
You multiply them together. So if you have x to the 4th to the 1/5, power to a power, multiply 4 times 1/5, that's 4/5. So that's one reason why we might write something using an exponent instead of the symbol, because it allows you to simplify a little bit. Any questions on writing a root as a fractional exponent? That's going to come up again later when we look at logs, okay, tomorrow in chapter 5. Yep.
So what's good in the box, and like x is like 4,
so if you had, can you just tell me again?
so there's like 10, like you said, so it'd be x of 10 in the box, and then like x4, so you can simplify that to like 5 over 10 outside, or?
Something like that?
Yeah.
So that would be x to the 1/10. Yep. And we'll talk about how do you type that in on the calculator. Well, if you type it as an exponent, you probably already know how to do it, but you can also type it in this way. There's a button on the calculator to do it.
And so, like, the x had an exponent on itself when it was in a radical, it would just, like, add to the, like, the exponent you have on the outside. So if x was to the 4th, it would become 5/10.
Yeah, yep. Because you'd multiply 4 times 1/10, which is 4/10, and then reduce it to 2/5.
Okay.
2/5. Because it reduces. Any questions on that? Okay, so when they ask you to solve a root problem, a lot of times they're going to ask for the principal root, which basically is just a fancy way of saying they want one answer. Because technically, if you do a square root problem, there are 2 answers. If you do a cube root problem, there are 3. If you did a 10th root problem, there are 10 different answers. But principal just means one answer. And there's really 2 cases we can look at. If you're doing an odd root, and the next one we'll look at is an even root. Okay, so if n is odd, basically what you're doing is solving this equation. Okay, and I'll make up an example and show you. Right, so I'm going to do an odd root. I'm going to do a relatively low. I'm just going to do a cube root. So let's find the cube root of 8. Okay, pretend like we didn't know what that was. What this is telling you in this that I labeled step 1, it's basically how you would explain to somebody how to do that problem. You would say, well, x, n is your index, x to what power would give you 8. That's how you would explain how to do it. What number do you raise to the 3rd power? And the answer comes out to 8. If you can solve this equation, which is basically what I have right there, that's the answer to what I wrote up above. That's what you have to figure out. So in this case, x to what power gives you 8? 2. Bless you. So when you take a cube root, that's what you should be thinking in your head if you don't know what cube root means. What to the 3rd power gives you whatever you're looking for, 8, 12, okay, whatever it happens to be. Now, could I do this? Is there a number I could raise to the 3rd power and get negative 8?
-2.
Negative 2, yes. Because negative 2 times negative 2 times negative 2 would give you negative 8. So the point there is when you have odd roots, negatives underneath are okay. Negatives underneath are okay. When you have even roots, one thing, if we don't want to deal with imaginaries, we have to make sure that the number under the root is positive. That's what this is saying right here. Whatever you're taking the root of, it's greater, actually it's not positive, it's non-negative. Okay, it's greater than or equal to 0. Okay, so let's look at kind of how that would work. Let's say somebody asked you to find the fourth root. So I picked an even. And now I have to pick a number that's greater than or equal to 0. 16. Okay, so let's find the fourth root of 16. How do you figure that out? Well, if you know it, it's a nice answer. Or if you don't know it, rewrite it in this format and figure out the answer. X to what power gives you 16? So I just replaced n. That was comes my exponent. Whatever's under the root ends up by itself on the other side. Okay, so that's how you would explain to somebody what a fourth root means. What number to the fourth power gives you 16? Okay, and what would be the answer in this case?
2.
Yeah, it would be 2. Yep. So now, could I do something like that? Could I put a negative in front of the 16? No. Right, it has to be non-negative. If it wasn't, it would come out imaginary. Okay, well, why does it have to be non-negative? Well, think about if you multiply 4 things together. They all have to be the same. So you could do a negative times a negative times a negative times a negative. Would that come out negative?
No.
No. So your only other option is to try a positive, 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 positive. Would that come out negative? No. So the only 2 possibilities you have to multiply 4 things that are the same, okay, they can't be different, they all have to be the same, would never come out to negative. That's why it always has to be a number of 0 or higher. Okay, so 1 and 2, I'm just kind of showing you ways you can think about cube roots and fourth roots if you didn't understand what they mean. It's basically like solving that equation. What to a power equals a number. Okay. All right, so let's look at specifically a square root. And I want to see what happens when I take a square root. If you take the square root of 4, what do you get? Yeah, you get 2. So what happened? Did it get smaller or larger?
Smaller.
In that case, it got smaller. Okay. Let's try the square root of 18. You get about 4.24. What happened that time? It got smaller. Okay, so it appears with the examples I've shown you right now, when you take a square root, the number gets smaller. How about the square root of 1? Is 1. So that didn't get smaller or larger, it stayed the same. So now we've got a number that proves if you take a square root, it doesn't always get smaller. Sometimes it stays the same. Let's look at this one. Anyone have a guess what's going to happen here? Yeah, it's going to get larger. If you put 0.5 and you press square root, you get 0.71 if you round it.
The closer it gets to 1, the square root of x gets bigger or smaller?
If it's less than 1. Yeah. If it's greater than 1, you take a square root, it'll get smaller. If it's exactly 1, it stays the same. If it's less than 1, it gets bigger. And of course, what if it's negative? We're not talking about negative because that would be imaginary. So what I just said covers everything. 0.2 square root, 0.45. So the answer, does it get smaller or larger? Well, it depends. Okay, what does it depend on? That's what I just said. So let's graph a couple even root functions so you can kind of see what they look like. Okay, to do a square root, you just do second square root. Let's also do a fourth root. So to type in a fourth root, you start with the index 4, press math, and then go to the fifth option down, and now it'll take that 4 and put it as an index in the root. So you put your index, go to math, fifth option, and let's just graph the fourth root of x. So the fact that sometimes you take the square root and it gets smaller, sometimes you take the square root and it gets bigger, is going to give us kind of an interesting comparison between these two graphs. Okay, so there's the square root, and there's the fourth root. Okay. It's kind of hard to see it, but what I want to do is focus on that section right there. I want to zoom in. I can kind of see that as if I head to the right more and more, the red graph is definitely under the blue one. Does everybody agree with that? Which means if you compare the fourth root of a number to the square root of the number, the fourth root is smaller as you head further and further to the right. But that kind of weird behavior that sometimes a square root gets bigger is going to cause something weird to happen in that box as far as what's bigger, a fourth root or a square root. Right, well, it depends. Let's zoom into that box and see. Yeah, they're going to cross each other. So let's just look at 0 to 3 and 0 to 3. I clearly typed something in wrong. 0 to 3, 0 to 3. Okay, so there's our square root. And there's our fourth root. So remember that idea that I said, at 1, if you take a square root, it gets smaller. If you're smaller than 1 and you take the square root, it gets bigger. So what happens is, that idea that I just mentioned causes these graphs to kind of switch places. If you take a square root, right, of a number that's between 0 and 1, the result is smaller than a fourth root. But if you go bigger than 1, it switched places. Now, if you take a fourth root, it is smaller than the square root. The red one is below the blue one. And the red and the blue are both the same at what number? 1. Okay? So that's kind of an important point. There's 2 points that all even roots go through. They all go through the point 1, 1. And they also all start at the point 0, 0. Now, that's assuming that you don't shift the graph. Because you could take that graph and you could bump it up 1 unit. Okay? If you shift it up 1, then everything I'm saying right now would shift up 1. Okay? Or if you shift it right 1 or down 1, that's different. But if you don't shift it, any even root you graph will always start at the origin and go through the point 1, 1. I think that's what I'm trying to show you in this picture. Okay, also, when I had it zoomed out, did this graph go in both directions, or did it just go in one direction? It only went in one direction. It only started at the origin and went to the right. That's because if you try to go left, you can't. If you try to go left, what kind of answers are you getting? Like if you try to take the square root of a negative, you're getting imaginaries. Okay? You can't do any numbers that go to the left. you can only do 0 as high as you want to go. So that means the domain is from 0 as high as you want to go. Okay, so for basic even root functions, functions that you haven't transformed, you haven't messed with in any way, the domain is 0 to infinity. Now, let me zoom back out so you can see the big picture again. Range, that's how far up and down the graph goes. Okay, it doesn't matter which graph you look at, these graphs have the same range. Do the graphs go down forever?
No.
No, they definitely have a point they start at. What does it look like the lowest they go is?
0.
Yep, the lowest is 0. And how about the highest?
1, 2, 3.
Well, let's look further over to the right. Let's go out to 40. So it definitely goes higher than 1 or 2.
Goes on forever.
It does. It keeps going up forever. It doesn't go up very quickly. But think about it. If you take a square root of a bigger and bigger number, does it ever stop going up? No. Like if you take the square root of 1,000, it's going to be smaller than if you take the square root of 1,000,000, because 1,000,000's bigger, right? It just keeps going up and up. It doesn't go up fastly. It doesn't go up fast, but it still goes up. So the range is 0 to infinity. Okay, and we're going to compare that to what happens when you graph an odd index, okay, like a cube root or something like that. Okay, so even roots, domain is 0 to infinity, and if you forget it, just think of the simplest case. Think of a square root and ask yourself, can I plug negative numbers into a square root? No. You can only plug in numbers 0 and higher. That's true for every even root. Okay. So any questions on those two facts? Okay, so let's look at odd roots. Okay, you know what I'll do first? Let me graph 2. Let me graph a cube root and a fifth root. And I think you'll see some kind of patterns. I want you to look for points that they have in common. Okay, so here's your cube root. Here's your fifth root. Okay, and I'll hit zoom 6 just to get the standard window. Okay, so what you're seeing right now, that's a cube root. Notice it goes in both directions, because you can take the cube root of any number you want, positive or negative. And there's the fifth root. Same basic pattern, a little different. But looking at that graph, does anyone think they see a point that would be common to all odd roots? Not just third and fifth.
0, 0.
Yep, 0, 0. Let me zoom in a little more. So 0, 0 is definitely one of them. Yeah.
Also, so you can pretty much take the roots of like positive or negative as long as the like exponent for the root is odd.
Yep.
Okay.
Yep.
1, 1.
Yep, 1, 1 is another point.
-1, -1.
And -1, -1. So those points are common to all odd graphs. And again, what we're assuming there is you don't transform it. If you take that graph and you shift it up, well, that's going to change what I'm saying. But that's just for the basic graphs. Okay, now domain. That's how far left and right the graph goes. Based on what I showed you, how far left and right do you think odd roots go?
Definitely.
Forever. And the idea is you can take the cube root, just one particular odd root. You can take the cube root of any number you want. Positive, negative, 0, fractions, decimals. It's not like even roots. You don't have to stick to positives with odd. And how about how far up and down?
Forever.
Yeah, forever. It's not going up very quickly, but it's going to keep going up very, very slowly. So for odd roots, the domain and the range is negative infinity to infinity. It's all real numbers. Okay, so the big thing to understand here is the difference. What I call is either the start point or the center point. Odd roots have what I call a center point. That's the center point right there. And from that point, they go in each direction. Even roots have a start point and go one way. So even roots start one spot, they only go one direction. Yep. And odd roots go in both directions. So let's look back at a square root. What do you think would happen if I put a negative in front of the square root? What does a negative cause a graph to do? Yeah, it causes it to flip. So instead of going up in this part, I reflected it down into that part. Okay? But it's still the same idea. It has a start point, just goes in one direction. What do you think would happen if I put the negative there? What do you think the negative there would cause to happen? Not imaginary. So what did the negative cause to do on the last one? Flip. That's still going to flip it. But it's going to flip it the other way. So instead of flipping it down there, it's going to flip it over there. So now it's curved the other way.
Wait, so what did you do when you do that?
I just put the negative under the root instead of outside the root.
What if you put it over 1 in the fraction?
If I did 1 divided by the square root of x?
You put the whole equation on top and put it over 1. Or put it over a fraction.
Put that on top and then like that?
Yeah.
That would look the same.
Oh, that would?
Yeah.
What if you put like 2?
If you put 2, then it would change it. We'll talk about how it would change it, but yeah, that would change it. Okay. So again, general idea, even roots, always going to look like one of those 4. Okay. If there's no negatives, it's always in quadrant 1. If you throw a negative in, it's going to flip it in a different direction. All right, so let's look at the transformations. That's what Evan was asking. The transformations are exactly the same as the transformations we've done for every other function we've studied all year. The stuff inside the function, okay, that I just circled, that's your horizontal stuff. The stuff outside that I just put boxes around, that's the vertical stuff. Okay, horizontal stuff is always inside the function. Vertical, always outside. Okay, so A, that causes your horizontal shift, left and right. Now B is going to be horizontal, but it's not a shift. What's the other thing we can do?
Stretch.
We can stretch. Horizontal stretch. Anytime you add or subtract, that's always a shift. Anytime you multiply by a number, that's always a stretch. So what do you think C would do? We're multiplying by a number, but it's outside.
Vertical stretch.
That's your vertical stretch. And D, you're adding or it could be subtracting, but it's outside the function.
Up or down?
So that's your vertical shift, either up or down. vertical shift. Now, with the horizontal stretch and the vertical stretch, with B and C, you could have a negative in there. What happens if you have a negative? That causes the graph to
Go down or go up.
And what kind of transformation is it? It's a flip. It's a reflection. So if B is negative, it's a horizontal reflection. What does a horizontal reflection look like?
Over the x-axis.
That's horizontal. So horizontal, yeah, you got to just be careful. Horizontal really mirrors it over the y. If C is negative, that would be a vertical reflection. Bless you. Vertical reflection. Actually, let's try it different. That's a vertical reflection. Vertical is when you flip up to down. That's over the x-axis. So you just have to keep that straight. Okay, and we've already come up with the order for writing the transformations, but again, if you don't remember them, actually the order is right there. A, B, C, D. That's the order you're doing them. Horizontal shift, horizontal stretch, vertical shift. Okay. And whether you're looking at a square root or a cube root or a fifth root, the root doesn't really matter. It's all the stuff, the A, B, C, and D that you have to focus on. Okay, so this particular one, we're comparing the square root of x to the square root of x minus 2. How many transformations are happening in g of x compared to that? Just one. There's only one transformation. I showed you all four up above, but this just has one. And that minus 2, we know it's a horizontal shift, but which way is it going to shift?
Right.
Yes, it's going to shift right to. Okay, we've talked about it several times. The horizontal stuff is always backwards. If you see plus, a plus under here would shift left. A minus shifts right. For the vertical, it's what you would expect. Positive is up, negative is down. Okay, but that's a shift right to. Okay, this one also is a just one transformation. And what are we doing this time? Yep, we're going to shift left 3. If you just said shift left, okay, I'd give you half. You got to tell me the direction and how much. Same thing if you just said shift 3. You got to tell me which way, down, left, or right. Okay, so that's good. Shift left 3. What's different about k of x? There's something different about the way that one is written.
It's flipped.
Yeah, what's under the radicand is flipped around. Anytime we want to describe transformations, you want x first, and then the number after it. So can anybody tell me how I can rewrite that? Yep.
Negative x plus 3.
Yeah, negative x plus 3. Now, you think, Andrew, could you tell me how many transformations are happening there?
Still 1. I don't know what the negative is.
Well, the negative is a second one. Well, we talked a little about it. We got to write that one as well. Follow the order. Start with A. Okay. Colin, what's A doing?
It would stretch to the right 1. Like you multiply it times 1 because there's a negative 1 for the x.
So when you have a plus, the number after the plus, is that a stretch or a shift?
That'd be shift.
It's a shift. It's a translation. And which way is it going to move? So Colin, which way is that one going to move?
It'd be to the left 3.
It's to the left, right? It's the same as the one above it for that part. Okay, plus 3 is shift left 3. Now, what about the negative in front of the x? Well, if you stretch by, let's break it down. Let's put the negative 1 in there. Is the 1 causing a stretch? No. If it's a 1 in front of x, it's not stretching it. But the negative is doing something. It's flipping it. So that's half of it. It's going to be flipping it. We just have to say over which axis. This is a horizontal flip. So if you flip horizontally, that means you had a picture here. That's horizontal. So yeah, you could say two things. You could either say it's a flip over the y-axis, or you could say a horizontal flip. Same thing. And instead of flip, you could also use the word reflect. But it's important to understand which axis is which. I know it doesn't quite make sense, but that's the way it is. Horizontal flip is over the y-axis. Vertical flip is over the x-axis.
Would it shift left first and then?
Yes. Yep. Sometimes the order doesn't matter, but for now I'm not going to get into that because it's kind of like PEMDAS. Sometimes you can switch the order and it's okay, but just stick with the ABCD order that I gave you.
Alright.
Yep.
The negative x is like a positive 2. Would that be reflect over the x-axis too? Or?
So if the negative x was a positive 2, like this,
Yep.
so in that case you wouldn't have any reflection because there's no negative. You would have a shift left 3, and that would cause a horizontal stretch or compression. That would actually be a horizontal compression by a factor of 2. All the horizontal stuff is backwards. Okay, when you see a big number for horizontal, you might think, oh, big number is going to stretch it bigger. Oh, big numbers actually make it smaller. Actually, let me graph that and show you. So, the square root of x looked like that. Square root of 2x would look, let me make it a different color. Red one. When you put a 2, you might think, oh, bigger number makes it bigger. It's going to compress it. So it would do something like this. Stay at the start point. That's a compression by a factor of 2. And graph it on here so we can double check. Okay, so in black, try to use the same colors. Square root of x. And in red, I tried to show you what happens if you compress it. Okay, so there's the compression, and there's the original, just like I drew. Keep in mind, these don't stop. They do continue on forever. I didn't draw them forever. So what do you think would happen if I did, instead of putting a 2 next to it, what if I put 0.5? That would horizontally stretch it. So that would take this graph and do something like that. It would stretch it out. Again, we didn't have a stretch in this problem, but that was just a question. So any other questions on that? Okay. So that diagram, or that little chart at the top is very helpful to figure out what the 4 numbers are doing. So that's good to have. Right, so last 2 things we're going to look at is drawing a little more accurate sketch than what I just did, like really using like graph paper and making a sketch. And the first thing you always want to do when you make your sketch is find the point that corresponds to 0, 0. For an even root, I call that a start point. For an odd root, I call it the center point. Any questions why I call it a start point for even and a center point for odd? Okay, so that's the first thing you have to find. Where does your graph start? Or where is the center? Right. Well, to find the x value of your start/center point, take what's under the root and set it equal to 0. Right, so just to show you an example, if I was finding the x value for the start point, I would take that and set it equal to 0, what I just circled. Okay, that gives me the x value. Then once I have the x value, that equation is y equals. If you plug the x value back in, substitution, you can find the y value. Okay, now at this step, you're going to have your start/center point, depending on what kind of route you're working with. Now we're going to use the graphing calculator, specifically the table, to get some more points. Now, I said includes points to the left and the right, if applicable. Okay, so why? Why if applicable? How come you don't always check points on each side of your graph? Yeah? Yeah, even ones don't go to the other side. So when you're graphing, sometimes you only need to check points on one side of your start point, because the other side could be imaginary. If it's an odd route, then you got to check both sides. That's why I wrote if applicable. Okay, so that's basically it for graphing. So let's look at a sketch. Okay, they don't ask for it here, but how many transformations are in that graph?
4.
It depends on how you break it down, but you could either say 4 or 5. Okay? You've got a vertical stretch and shift happening. You've got a horizontal shift, horizontal stretch, and that negative is also a reflection.
Oh, yeah.
So it's not written in the right order. I would put negative 2x plus 3, but there's actually 5 separate things happening. Okay, but the point on this one is to graph it. Is this the kind of graph that's going to go both directions or just one? Yep, it's going to go in both. So step 1, set the x, to forget the x value, set the radicand equal to 0. 3 minus 2x. Set it equal to 0 and solve. What do I get for x when I solve that?
3 over 2.
Yep, 3 over 2, or you could also put as a decimal
1.5.
1.5. The only reason I suggest the decimal is because we're graphing. And that might be easier. Okay, so that's my x value. What do I do with that number to get the y value?
Plug it back in for x.
Plug it back in. Okay, so let's plug in 1.5. What's 2 times 1.5? 3? What's 3 minus 3? 0. Well, we already knew that it was going to come out to 0, because that's what we just solved. So when you plug it back into the radicand, you should always get 0. That's what we did. And then what's the cube root of 0?
0.
0 times 2?
0.
Still 0. So the only number that really matters is that. What's 0 plus 1? 1. So that's my center point. So our xy table, that's the first point in. Okay, now I'm going to type in the equation. Use the table to get a few more points. Now we already said this, but should I be checking points above and to the left and to the right of 1.5, or just on one side? I got to check both. All right, so type in 2, and here it's important you put the time symbol and then a 3, because if you don't do it that way, when you press what I just pressed, it would have put the 23rd root. So you have to separate the 2 from the 3 so it knows the 3 is the
Wait, what's the time symbol?
right below division.
Oh.
Yeah. Okay, so any question on that? You have to type it that way. +1. Okay, let's check 1.5 and see if we get 1.51. All right, so if I type 1.5, I get 1. Yep, that's good. Okay, if we type 1.5 and we don't get 1, then that means we solved it wrong. Okay. Now, because my graph paper is only going to go -10 to 10, I'm going to just try a few points up to 10 and as low as -10. So let's do maybe 5, 8, 10. I'm going to write those numbers in the table. Let's do -5, -10. I'm going to throw 0 in there. It's always good to find the intercept. It's just another good point. There's your table. Now graph those points. If you need more points, you can, but generally for an odd function, 6 points is pretty good. All right, so let's see what we got. We got 1.5, 1. We've got 5, -2.8. Let's see, 10, -4.1. And I think I had one more in there. What I have? 8. Yeah, 8, -3.7. All right. So on that side, I can see the curve pretty good. Let's check on the other side. So -5, 5.7. Let's see. -10, we've got 6.6. Okay, and from those points, it gives me a pretty good idea of the sketch. Okay, so just connect it, and that's it. That's your picture. Yep. Good enough. So the point is, it's an odd root. It goes in each direction. Oh, I also had 0, 3.8. I didn't even graph that one. So that one's actually helpful because I think it shows me how it curves in the middle. So I think I had the curve a little too smooth. It's a little sharper of a curve. A little more like that. It's always good to get a good amount of points near where it actually curves in the middle so you can get an idea of how sharp it should curve. That's how you graph an odd root. That's probably the harder of the two roots because you've got to check points on each side. With an even root, you only check them on one side. And the way you figure out which side to check, well, if you check one side and you get errors on the calculator, check the other side. Any questions on graphing odd roots? All right. Okay, so the last thing we're going to look at is solving equation. Okay, most of the equations we're going to look at are algebraic. I might do one graphical at the very end. Okay, so to solve a radical equation, the idea is you have to get the radical by itself. Okay, I'm going to show you a problem where the radical is by itself, and then I'll show you one where it isn't. That's a problem where the radical is by itself. It's already on the left-hand side, all of them. That's a problem where the radical is not by itself. Okay, there's two of them on the same side. You've got to put one over on the other side. Okay, so get a radical by itself. In the problem I just showed you where there's two of them, it doesn't matter which one. Just get one of them by itself. And then once you isolate one of the roots, you're going to raise each side to a power. If you're dealing with square roots, you're going to end up squaring each side. If you're dealing with cube roots, you're going to cube each side. Because the idea is to cancel out the root. You would probably, for the ones that work out to be a little longer, I would never give you anything worse than a square root. Because if I do, they start to get pretty bad, okay, with the multiplication. And you always have to check for extraneous solutions. Okay, because when you start raising both sides of an equation to a power, it's not that it's wrong, but you can change the equation in a way that you create an extra answer that shouldn't be there. So you always have to check for extraneous solutions. Okay, I'm going to start off with one where the root is already by itself. Okay, it's the cube root of x squared minus 2x plus 2. Now, if I'm writing solve algebraically, this has got to work out nice somehow. Somehow it's going to factor, or that the numbers are set up to make it work. Because if you just pick any numbers, you're not going to be able to solve this with algebra. Okay, so step one, isolate the radical. That's done. Next, raise each side to the power of the index. Michael, what's my index in this example? 3. So I'm going to cube each side.
Thank you.
Right, so we're going to cube what's on the left, cube what's on the right. Casey, what happens when I cube what's on the left?
Squaring out.
It cancels
Having the cube root.
the cube root. So when you cube, those two things cancel each other out. Now you have that. Okay, and the goal here is going to be to factor it. So anytime we factor, we try to get it equal to what number? Ezekiel?
0.
Yeah, we're going to get it equal to 0. Okay. When I factor, I like the highest term to always be positive. So I'm going to take everything that's on the left and move it to the right. You could move what's on the right to the left, but I think it's going to be harder. So move everything that's on the left to the right. So we get x cubed. I'm going to subtract the x squared, add the 2x, minus the 2. Now, when we factor with 4 terms, it's a special kind of factoring. Does anyone remember what that's called? Grouping. Yes, factor by grouping. And the hope is that if you factor something out of the first 2 and the last 2, something special happens. What can you factor out of the first 2?
Squared.
X squared. If you do that, you'd be left with x minus 1. Now the goal is we're going to have to be left with an x minus 1 in the other part where it's not going to work. Anybody see what I can factor out of the second part? Yeah? 2. And what does that leave me with if I factor it out?
X minus 1.
It does leave me with an x minus 1. And now, if you look at each box, what's common to each one?
X minus 1.
X minus 1. So I'm going to factor that out. If I do that from the first box, what's the only thing that's left?
X squared plus 2.
Yep, x squared. And then if I do it from the second box, I'm left with a plus 2. Now, we're multiplying something times something, and we're going to get 0. What's the only way you can multiply 2 things together and get 0 is the answer?
By 0.
If what?
If it's by 0.
Yeah, if you're multiplying by 0. Either one of them or both of them are 0. So, set the first one to 0. Set the second one to 0. Caitlin, what do I get if I solve the first one?
8.
Yeah. 1. Yep. So x equals 1. We'll check to make sure it's not extraneous. Now, look what happens if I start solving the second one.
It's imaginary.
It would be imaginary, right? My next step here would be to take a square root, and I can't do that. That's imaginary. So we don't have to worry about any answers from that part. So let's just check if 1 works. Just so we can see the original problem a little clearer. Just gonna move all that stuff away. So if we plug in 1, what's 1 squared? 1. 2 times 1? 2. What's 1 minus 2?
1.
Negative 1. Plus 2? 1. And what's the cube root of 1? 1. So we get 1 on the left. If we plug 1 in for x, we get 1 on the right. Do they match? Yep. So that answer works. So the answer is x equals 1. Okay. Any questions on that one before we do last one? All right. This one I'm not going to solve graphically, I'm just going to do it with algebra. If you wanted to do it graphically, it's actually very easy. Just type all of that into y1, type that into y2, and what would you look for on the screen? Yep. Look for the intersection, just see where they cross. That's all you'd have to do it graphically. All right, so to do it algebraically, what's the first thing I have to do? Yeah, Ezekiel?
Isolate one of the radicals.
Yeah, I would isolate one of the radicals, and I think the easiest thing is to put that one on the other side. How would I move that to the other side, Ezekiel?
Plus.
Plus, yep. Right, so now on the left, that leaves me with square root of 6x plus 12. And on the right, I have 1 plus square root 4x plus 9. Now, I'm going to be able to get rid of that square root on the left by doing what to each side? Yeah, Andrew?
Square equals to 0.
Sorry, Andrew, yeah.
Make it equal to 0.
Not getting equal to 0. Dave, do you want to say?
Squaring by the index.
Yeah, you're going to square by whatever, well, in this case it's 2, so we're going to square each side. Okay. Any question on why you're going to square? Okay. So square here and here. Before I do it, I just want to go back and look at the directions. Raise each side. Okay. So that means when you do this, you can't just square the 1 and square the 4x, square root of 4x plus 9. That's squaring the terms. What it means to square each side is to do this. You can leave it with the exponent of 2. I just think some people might like to see it written out like that because it shows you what we're about to do. On the left, that side is easy. You've got a single square root, you're squaring it, square root's gone. But what property do I have to use on the right?
Distributive.
Right, you have to use distributive. So start with 1 times 1 plus, you have 1 times the square root of 4x plus 9, another 1 times the square root of 4x plus 9. So how many square roots of 4x plus 9 do we have? 2 of them. Square root 4x plus 9 plus another square root 4x plus 9. That's the part people miss sometimes. Last part, positive times positive. Let's take care of that first, it's positive. And what's the square root of 4x plus 9 times the square root of 4x plus 9? Or you can think of it, you're basically doing this. You're multiplying the square root of 4x plus 9 times itself. Casey?
Is it just
It's just 4x plus 9. So if you've done the second step right, when you look at it, I mean, there's a lot of like terms to combine, but there's only one root left. Okay, let's combine some like terms. There's really nothing on the left, but on the right, does anybody see some like terms I can combine?
The 4 and 1.
Yep, the 1 and the
Oh, 9.
9. What's 1 plus 9? 10. So combine that together. So I get 10 plus 4x. Everything else stays the same. Now my goal is to get that by itself.
So you subtract 4x.
Subtract the 4x. Yep. What else?
10.
Yep, and let's just do that for now. So that's going to give me
2x plus 2.
2x plus 2 equals 2 square root 4x plus 9. There's one more thing we have to move, that 2, and how do we get rid of that?
Divided by 2.
Divide everything by 2. That's gone, that's gone, that's gone. So we're left with x plus 1 equals square root of 4x plus 9. Now we have the root by itself, and it's a lot simpler than what we started with. What do we do on both sides now?
Subtract 1.
No, we want to leave the 1 where it is. We got to get rid of that root. Square it. So I said sometimes you have to square each side twice. This is a problem where you have to do it twice. Basically, however many roots you start with, that's how many times you're going to have to raise each side to the power. But this time, it's going to be a lot easier than it was last time. Okay. What do I get on the right when I square that? Yep.
X squared plus 2. Or x squared plus 1, sorry.
So on the right, yeah, we get 4x plus 9. And Colin, what were you saying about the left?
The x squared plus 1.
I agree with the x squared and the 1, but we lost something. Remember, x plus 1 squared means this.
Oh, 2x.
Yes. X squared plus 2x plus 1. And now we don't have any roots left. What kind of equation is that? It's a quadratic equation, and when we solve a quadratic, we always get it equal to 0. Subtract your 9. I would subtract the 4x at the same time. 2x minus 4x would give me
Negative 2x.
negative 2x. And what's 1 minus 9?
Negative 8.
Negative 8. If it's factorable, that would be ideal. If not, then you'd have to use quadratic formula. Two numbers that multiply to give you 8 and subtract to give you 2.
4 and 1.
Yep. Let's try a negative 4 and a 2. That gives me plus 2x. Take away 4. Perfect. Negative 2. What would make the first factor 0? 4. And the second factor?
Negative 2.
Negative 2. Now, I just have to make sure that those both work. Let's check 4. 6 times 4?
24.
24 plus 12? What's the square root of 36? 6. 4 times 4 is 16 plus 9.
25.
What's the square root of 25? 6 minus 5. Does that equal 1? Yep. So that one works. Let's check negative 2. 6 times negative 2 is negative 12 plus 12.
0.
0. 4 times negative 2 is negative 8 plus 9. 1. What's the square root of 1? 1. Does 0 minus 1 give you 1? No. No, that is correct. It's 0 minus 1 equals 1. We didn't do anything wrong It's just that answer is extraneous. Okay, so always double check. Make sure your answers work. Okay, homework tonight. It's on 255. It's not really a ton of problems, just a little bit of graphing, a little bit of solving equations. 5, 6, 12, 14, 20 to 22, and 28, 31, and 35.